spectrum of ethanol. And what I want to focus on, there's the hydrogen on the oxygen. And you'll notice, it still isn't very well focused, is it?
You can zoom too, can't you?
Yeah, I'm just about to do that. Okay, that's a little easier. Here's the hydrogen on the oxygen, and you notice that there are two hydrogens on the carbon next door, so you expect this to be split into a triplet. And there it is, split into a triplet. Okay? Now, if you take the spectrum, this is ultra pure ethanol. If you just take ethanol out of a container, common ethanol, which has very small amounts of acid or base impurities, notice that the splitting here is gone. Okay, and what's happening is in the presence of acid or base, it catalyzes this proton coming on and off and on and off and on and off and on and off. Okay, and if it's coming on and off and on and off at a frequency that's higher than the frequency at which this thing resonates, it decouples it. So when you see hydrogens on oxygen or nitrogen, it is very typical for there to be no splitting, and you'll notice that these no longer split these. This thing is now a simple quartet, split by those.
Can you scroll back up to the, yes. So there's an example of splitting and then chaos.
Yeah, this is a complex splitting pattern because this thing splits these into a quartet, and this thing splits each one of those peaks in the quartet into a doublet. And they don't necessarily overlap. So you get this complex splitting pattern. But as soon as that proton comes on and off and on and off, the coupling disappears. This is unsplit, and this is just a common quartet. So when you've got hydrogens on oxygens or nitrogens, sometimes the splitting is not there. And I told you that that happens if this thing is coming on and off at a frequency that's substantially greater than the frequency at which this thing resonates. There's another way to change the speed at which the thing comes on and off, and that is to change the temperature. So here is a series of spectra of ethanol at different temperatures. Okay? And you'll notice that, look what happens to the splitting. This is minus, whoops.
The other way out. There we go.
This is at minus 40 degrees. So the hydrogens on, this is methanol, the hydrogens on the oxygen are coming on and off very slowly, at a frequency less than this resonance frequency. And as you slowly heat up, you see those peaks broaden and broaden and broaden and broaden until finally, way down at the bottom, it's at 31 degrees, it's become a singlet.
And has that big wave also, that peak also changed too? Because
Yeah,
at the top
look, this is now a singlet too.
Right.
There's no splitting now between the hydrogen on the oxygen and the hydrogens on the carbon, but as the temperature goes down and down and down, the splitting slowly gets there until finally the hydrogen on the oxygen is a quartet and the hydrogens on the carbon are a doublet.
So generally, the higher the temperature, the less splitting.
Well, for hydrogens on oxygen or nitrogen.
Oh.
Yeah, because those are the hydrogens that hydrogen bond, and it's that interaction in the presence of either a very tiny amount of acid or base or a high enough temperature that those protons come on and off and on and off the oxygen. It does not happen with protons on carbon, only on oxygen and nitrogen, only on the atoms that can hydrogen bond.
It's kind of like they're loosely held.
Yeah, it's like they're loosely held, but what it is more is they're just coming on and off and on and off and on and off. You know, it's like you can see this, and if I got this going fast enough, you'd have trouble seeing the difference. Yeah, it would just look like a blur.
So hydrogen, H bonded hydrogens
Yes.
with are affected by temperature and acid and base.
Yeah, yeah. But the thing, all you have to remember is that if you're trying to interpret a spectrum or predict a spectrum for a compound that has hydrogen on oxygen or nitrogen, you may not see the splitting that you're used to seeing.
Okay.
You may see something that's, you know, ugly looking like this. What the heck's that? Well, this is happening because the hydrogen is coming on and off at roughly the same frequency at that it resonates. Okay. Let's see what we can do. Okay, let's see what we can tell about this. Now, in case you can't read them, this is the integration. And this from here to here is 3, 2, 2, 2, 3.
Three, two, two.
Yeah. This is from here to here, that's 3. From here to here is 2. From here to here is 2. From here to here is 3. Okay, so let's look at this. We have the molecular formula. So first thing to look at, if you've got the molecular formula, is there any unsaturation? First thing to look at. 2 times 4 plus 2 is 10, so this thing is unsaturated. It's saturated. No double bonds, no rings. Okay, what else can we tell? There are 4 carbons. There are 4 peaks. So the hydrogens on those carbons are not equivalent. There are not 2 carbons that look alike. Okay? This thing is a singlet and unsplit. This thing has 1, 2, 3, 4, 5, 6, but it's asymmetric. So there's something going on here. This is a classic quartet. And the higher side is this side, so it's being split by something down here. And this is going this way, so it's being split by something down here. Okay, so the upshot is that these 2 things are splitting whatever's under here, and that's why we have a complex multiplet. Okay, so now, how are you going to arrange 4 carbons and 10 hydrogens and 2 oxygens to give you a spectrum like that? Now you have a copy of the spectrum, so I'm going to make it smaller. Put it up the top of the screen. Shade the bottom of the screen. Lift that. What can you tell me about that?
There's at least one set of methyl protons.
Yeah, this is right around 1 part per million. It integrates to 3. And by the way, 3 plus 2 plus 2 plus 3 is 10, and that's how many hydrogens we got. So there are 3 hydrogens in this peak, 2 here, 2 here, and 3 here. Okay, and this is not regular, so what I'm guessing is that there are 2 different hydrogens under here. group of 2 and a group of 1. Okay, so now, just based on this, integrates 3, it's split into 2, so I'm thinking that fragment has to look like this. That would account for the methyl group, split into a doublet. You can't have a hydrogen here, you can't have a hydrogen here. We've got 2 oxygens.
So
Do we have an alcohol or an ether? We cannot have a carbon-oxygen double bond because the thing is saturated. Ether or alcohol? The thing that tells you it's an alcohol is this resonance right here. It's about where an OH proton goes, and you see how broad it is at the bottom compared to all the other peaks? There's no splitting there.
Well, yeah, and also I think, or maybe I'm misremembering, that it doesn't have the clean line that kind of comes down.
Yeah, it's not split.
Right.
It's not split, but that's normal for alcohol. So what we're going to assume is this is an alcohol, and there's decoupling going on.
What he's saying is that it doesn't dip below the line.
Oh yeah, yes. There's not. This is called the ringing. That dip below the
Yeah,
line.
the
The ringing. There's no ringing. Yeah, and that's also because this is not a sharp peak. It's a broad peak. It's got 2 hydrogens under it. So if we got an alcohol, what does that mean? With 2 oxygens and we have an alcohol, you got 2 OH groups. Okay. So if I put a carbon here,
I went OH there.
okay, OH. Okay, that would explain, let's see, that would be this peak. This one is not split by that. And this is not split by that. So we got to have a carbon here, and there's only one other place to put a carbon. So we've got a 4-carbon chain. Okay, so the only question is, where is the other OH group? If we put the OH here, is that consistent with that spectrum? What you notice is this methyl group and this methyl group are equivalent. They look exactly the same. If that's the case, they should give a single resonance split into a doublet because each one has 1 integer. But that can't be because we've only got 3 hydrogens in that first peak. What about if we put the OH here? Now what would we have?
So now you don't have, they're not mirroring, they're not the same.
Now they're not mirror images. These 3 would give 1 peak. These 2 would give a different peak, integrating to 2. These would give a peak, integrating to 2. And these would give a peak, integrating to 2.
3, 4, 5, 6, 7, 8. I kept 1, 2. I mean, isn't there 5 sets of protons there though? Where
Yes.
you've drawn it?
And 2 sets are under here.
There's 2 sets under there?
Yeah, that's not a regular, yeah.
There's an
I thought
irregular.
there, yeah.
I thought there was only
2.
4 sets showed mud in it.
There's only 4 different resonances. This, and
1, 2,
this.
3,
If they were all, split symmetrically.
So for the last one, that's,
This is a complex multiplet, and there's 2 ways that can arise. And that is if the splittings are not simple, or if this is 2 peaks. For example, this might be a triplet, and this one's sitting right on top of a quartet, for example. So if two different hydrogens have very similar chemical shifts, but when they get split, those two split peaks might sit right on top of each other
And give you that.
and give you a complex multiplet.
So that complex multiplet, you're looking at, so from right to left, the second carbon, that hydrogen, and the final, the fourth one, those two. Is that what you're saying the complex one is?
This one is that doublet.
Right.
Okay. These two would integrate to 2 and have 1, 2, 3 neighbors. So these two should be a quartet.
Okay, so that's the next.
There's the quartet. The OHs here and here should give
That broad one.
that broad one that integrates to 2. And what's left,
On the alcoholic carbons.
1, 2, 3. This one will be split into a triplet. This one, 1, 2, 3, 4, 5 neighbors, would be split into a sextet. This hydrogen is on a carbon attached to oxygen. These hydrogens are on a carbon attached to an oxygen, so they have similar chemical shifts. So it's not surprising that the peak due to these two and the peak due to this one should be very similar in chemical shift, should be very close to each other. This will get split into a triplet, and it looks pretty much like we got a triplet right here. I mean, these three lines look like they're a triplet, except that one's too big. That one, excuse me, that one is split into a sextet. 1, 2, 3, 4, 5, 6. So if the middle of the sextet is right there, you're going to get something that looks maybe like that. You can't tell for certain. There's a way to analyze these things. You put in values for the coupling constant, and you program a computer to figure it out, and it figures out, okay, what's under here. But that's advanced stuff. Yeah.
Does it matter whether the OH is, the second OH on the right there, whether it's down there or
No,
up to the,
no,
it
no.
doesn't matter, right?
No, just rotate about this bond,
Right.
and it'll go to here, and then to here, and then back to there. Okay, given that structure, does that spectrum make sense? Okay. How about this one? C2H7NO.
What do you do for the element of unsaturation?
Oh,
When it's-
a nitrogen is like it's a half a carbon. The nitrogen has 3 valences, so it adds an extra nitrogen, an extra hydrogen. So it counts as a half a carbon.
So it'd be the 4 plus 2, or 4 times 2, 2 times 2 plus 2 plus 1.
Plus 1,
So
yes.
that's where we get in 7.
That's where you get the 7. So that thing is saturated.
Okay. And then the integration numbers, that's how many hydrogens are in those peaks?
If they add up to the total number of hydrogens, yes.
They do.
Yeah. Okay.
If they don't, what you do is there's just a little mathematical manipulation that you can, if you know the total number of hydrogens and you know the relative areas, it's not hard to figure out what the proportions are. And can you see the integrations? You read the integrations on your sheet?
2, 2, 3.
2, 2, 3.
It's fully saturated.
Question, I'm a little lost on this one. So when you're counting neighbors, so do you just go like one carbon over?
One carbon over, one atom over.
Well, one atom, so if it was a nitrogen or whatever.
Yeah, if it's a nitrogen, the hydrogens on the nitrogen can split the hydrogens on the carbon that it's attached to.
Okay, and so for a triplet, you have two neighbors, and the integration tells you how many have the same amount of neighbors.
How many? The integration tells you that this peak is due to two different hydrogens.
Right. Okay. Yeah.
This is due to two different hydrogens, and each one of those pairs of hydrogens have two neighbors.
Right.
So then there's three sets of peaks there, right?
Mm-hmm.
So that each sets of peaks are representative of hydrogens that are around a particular atom.
Yeah. Yes. These represent a particular one subset of the hydrogens in the atom. And
Right.
all of these hydrogens, this is very regularly split. And you notice that this one points this way and this one points this way. So if this is two hydrogens and this is two hydrogens, and they're splitting each other, they got to be next door.
Well, yeah.
If these two hydrogens are being split by these two, you should get a triplet. And if these two hydrogens are being split by those two, you should get a triplet. Okay? And what do you make of this thing?
That's more hydrogen. The what?
Now, alcohols are around here. That's wide.
They
Yeah.
had a really, I thought alcohols had, I don't know what the range of alcohols are, but when I was trying to look at it on the sheet, it looked like it had a really wide range.
Yeah, alcohols do have a really wide range.
Okay. So if I looked at that, I would think that it was an alcohol.
Okay, and what you would do is you'd try putting an OH group in that collection of atoms to see if you could make a molecule that would give you this spectrum. What I'll tell you is, if there's an OH group on there, I should have a peak that integrates to 1. I only have one oxygen in there, and there isn't. A group of 3, your first suspicion when you see a group of 3 or 6 or 9, methyl groups. One methyl group should integrate to 3, 2 to 6. 3 equivalent methyl groups should integrate to 9. So this that integrates to 3 should be a methyl group, right?
Did we cover integration
I don't know what
last
that-
Friday? I
Yeah.
don't think we did.
We
We
did.
did.
We just
It was
don't
like
know
very
this.
briefly though.
Well,
right?
it's just like, hey,
This
the
is,
number of
Yeah, here's the integration.
is your number of hydrogens.
you don't even know.
So-
Shit, last time we did Brandon's sums and stuff.
Two protons on a carbon
Don't talk about
where the
this.
neighboring atom has 2 produces a triplet.
Yeah, 2 triplets, assuming that those are the only 2 neighbors that each one has.
So the triplet at 3 is from, are we going to say that that would be like the 2 hydrogens on a carbon, and then the one at like 3.7 would be due to 2 on a nitrogen?
Yeah, these are 2 hydrogens. That's 2 hydrogens, that's 3. And what I'm going to start with is saying, okay, since I've got 3 hydrogens here, my first guess is a methyl group. Anytime I have a multiple of 3, my first guess is a methyl group. Okay, so I've got a methyl group. It's unsplit. So it has no neighbors.
So is it attached to the oxygen?
Let's try it. That would be consistent with this thing being so far down. Normally a methyl group and an alkane is over here about 1 part per million. This is way downfield. The oxygen attached to that carbon would explain that. Okay, so now we've got to have something else on that oxygen. We've got 3 hydrogens on this carbon, so we're done putting stuff on this carbon. We have another carbon and a nitrogen.
So you've got the CH2 and an NH2. Does it matter which order?
What do you think?
Oh, wait, no.
No, that's not going to work.
Nitrogen.
So yeah, you have to have the nitrogen on the end.
But
That will work.
I was just having trouble figuring out if they were, I don't know. I guess I would have to look at the sheet. Like, I don't know what the chemical shift of NH2.
and you notice, the only time I used the chemical shift, the only time I thought about the chemical shift was when I said, okay, I got a methyl group here and I'm going to put an oxygen on there. That should bring the chemical shift of this thing downfield.
Which you didn't even necessarily need to do that, because if you try and do, if you put that oxygen in the center or like in between the carbon, it comes out with a completely different spectrum.
Yeah,
It
that's
comes
exactly.
out with different, you can't have those, you won't end up with those triplets. Or
That's
those
correct.
quartets and all that.
Okay, so there is not a series of steps you can follow automatically. What you do is you take a look at this thing, you look at how many groups of carbons you have, you ask how they're split, and then you start fooling around with fragments of the molecule until you come up with one that gives you the spectra you've got.
So that which series of peaks is the NH2?
The NH2 is most likely this one because N is more electronegative than carbon, and that's going to de-shield these protons more than the carbon de-shields those two.
Okay.
But that CH2 is going to be shifted to the left by both the nitrogen
that's
and
true.
the adjacent
That's true.
oxygen, right?
So it's not abundantly clear, it's not obvious which one of the peaks belongs to which one of those pairs of protons.
But we could like look that up though,
Yeah,
right?
but right now everything's shifted because
Yeah, but you don't need to because this is the only thing that's consistent with that spectrum.
If I had to guess, I would put the CH2 at 3 and the NH2 at 3.7.
Yeah, but it's not obvious because this carbon is attached to that oxygen, which is more electronegative than the nitrogen. You know, and chemical shifts, the range that chemical shifts can be in is rather broad. So, I wouldn't bet the farm
Okay.
on which is which, unless I cheated and knew.
I would put the nitrogen because it's only one
Yeah.
thing that's affecting it,
Another one
whereas
is like-
it has 2 things that are.
Fair enough.
Okay?
Who cares? I don't know.
The shifts aren't good for determining what it is.
Right.
It's better just to go from, you start from look for
Big peaks with nothing else on it.
and
So something splitting it.
Yeah, something splitting.
So,
This
yes.
is what Eddie's supposed to
Here is compound 1.
Yeah. So this is huge.
But it's like saying, oh, okay, well, there's two neighbors. But there's one.
Yeah. Hey, we have
Ooh.
IR.
Hey, anytime.
Yeah.
Okay, and you also have a molecular formula, C8H10O.
Okay, so we have the OH.
Oh, great, this is so fun.
Okay, you got the alcohol.
Yep.
Can we assume that it's just a benzene ring, or do I have to try and?
I would start with a benzene ring. Anytime you've got 4 or more degrees of unsaturation, start with a benzene ring.
It's just, I cannot tell based on the.
It's right around 700. There's a big peak
Are
there,
you
700.
serious? I
Yeah.
can't figure that out.
Well, but now look at the hydrogens, look on your list and see where the hydrogens on a benzene ring are. What's their chemical shift?
7.2.
Huh?
7.2
Oh,
on
The
the NMR.
hydrogens attached directly to the ring.
Right.
that's what those are right there.
Yeah.
And
I
why,
would say that's pretty close to 7.2.
and why are there 20 of them?
There aren't 20 of them.
That's just the
Oh,
integration.
2.0. Yeah, 2.0, 4, 4, and 12. Oh, no, yeah, no. No, 4, 4, yeah, and 12. Wait, no,
That's a 20.
that's a 20. That's a 20.
So in this case, it has nothing to do with the number of hydrogens.
No, that's, yeah, and in this one, they haven't figured out for you how many hydrogens are under each peak. So let's do that next, okay? All of those, there's 20 and 4 is 24, 32, 44. So the total height is 44. I've got 10 hydrogens total. So each hydrogen must be 4.4, about 4.4.
I'll just do it like that.
Wait, what?
There's 40 numbers. And
Yeah, if you add up all the heights, it comes out to about 44.
how's it 44? It's 40.
Oh, 40, right.
Yeah.
20, 24, 28,
So the
38,
each
40.
hydrogen is worth 4.
So each hydrogen is worth 4. So that means that first peak has
5,
5 hydrogens, 1 hydrogen, 1 hydrogen,
3.
3 hydrogens.
Okay.
The degrees of unsaturation, 8 times 2 is 16, and 2 more is 18. We have 10, so we have 4 elements of unsaturation. Sounds like a benzene ring to me, and this thing pretty much
Is
settles it.
Can you explain what you were doing there? I kind of missed it.
Oh, I added 20 plus 4 plus 4 plus 12. That adds up to 40.
Okay.
And I know from the molecular formula that I have 10 hydrogens.
Okay.
Okay? So each of those hydrogens must equate to 4 units in the integration. Because 10 times 4 is 40. That make sense? Okay? So this is 5 hydrogens. What does that tell you?
It's a ring.
It's,
And what do you know about the ring if there are 5 hydrogens under this
Benzene
peak?
ring.
It's got one
It's
alcohol, one group.
mono-substituted.
Oh, that would be that.
And that would be this thing right here, and there's going to be another one up there. This is not a very good IR spectrum, but it's got enough information to tell us what we need. And basically what it tells us is, here's 3,000,
Some above, some
so
below.
it's got CH stretches above and below 3,000.
So there's a alcohol.
It's an alcohol,
Some-
and it's an aromatic ring, which is consistent. So we've got an aromatic ring that takes care of 6 of the 8 carbons.
There's a right
Okay, you guys have this in front of you, so can I do this?
there. Yeah.
Okay, so we have a benzene ring. With 5 hydrogens on it. And it's substituted in one place, so I must have two carbons here. I've already taken care of all 4 degrees of unsaturation, 3 double bonds in a ring. So we have 4 elements of unsaturation. So that has to be a single bond between the 2 carbons.
Does it?
We know it's an alcohol, so there's an OH someplace. The OH has to be either here or here. So there are 2 possibilities. Is that consistent with the spectrum?
Yes.
Yes.
Yeah, because the methyl group is split into a doublet. So it can only have one neighbor.
And there's 3 hydrogens together.
And there's, yes.
Right.
And this integrates to 3 hydrogens, and it's split into a doublet. 3 hydrogens with one neighbor. Okay, we're not sure whether these 2 are coupled. If there's no splitting between this and this, that should be a quartet. If there is, this should be a mess. We got a mess.
And it's a mess because it's influenced by.
Yeah, it's a mess because it's split by these,
And also the
and
ring. Would it be split by the ring at all?
no, it's not. No, no. If these are coupled, they should be 2 doublets.
I don't know what we're talking about. I don't know what's going on.
Okay, so one of these
We're looking at
is this, and the other is that, because they each integrate to 1.
Right. Which one is which, though?
Well, where do alcohols resonate?
Oh, just right in your belly.
They warm the tummy. A little above 4.
Yes. Well, 2 to 5, depending.
2 to 5, yeah. This thing, they don't show. That looks kind of like a doublet.
Is that a methyne?
It looks like a doublet.
Methine would be, yeah. No, actually not. A methine would be if you only have a CH. I don't know how they classify that.
I mean,
Methylene or methine. Methylene groups are usually CH2 groups, so yeah, I guess it would be a methine, but it's not a triple bond.
no, it wouldn't be, because they show it as an alkane with methine with just a C to 3 R's and then a single H.
Yeah.
And that's at a 1.4. So it's shifted.
Okay, so there is some. I am going to guess. Normally, a hydrogen is only split by the hydrogens on the carbon next door. But you remember when I was talking about complex splitting patterns? The effect of this hydrogen is much stronger if it's connected by a double bond. So there's a tiny amount of splitting from this hydrogen and this hydrogen to that one.
Even through another carbon?
Yeah, it'll be very small, but this thing can be split slightly by those 2. It's also split by this. So my guess is that this thing is that right here.
That little.
Yeah, and since if that's the OH, it's a doublet. So that means this is being split by this, which means this must be being split by that. So it's being split by this, it's being split by this, and maybe a little bit by these. So it's a mess.
Okay. And then,
Complex multiple, excuse me.
so wait, then the OH is the one that's like
Yes.
Okay, so we're going by that, okay. You said this above 4, and then.
Yep. But that's not consistent with the splitting. And I pay less attention to the chemical shifts than the splitting and the integration. The splitting and the integration are exact, the chemical shifts are not.
But they seem pretty easy to just.
Yeah, especially for alcohols. Yeah.
But when we're talking about just the values for chemical shifts, the methine is a lot lower than the alcohol normally. So if you're gonna see a shift,
Yeah, but this
anyway,
is not the methine you're looking at. The methine you're looking at, this thing is attached to 3 carbons. That's an oxygen.
okay.
And this thing also is probably influenced by the ring current.
But couldn't you say the same thing about the hydrogen that's hanging off the oxygen too? I mean, that oxygen.
This thing has only one neighbor.
Period.
Period. Right there.
Okay.
There's nothing there, and this is a single bond. So if this is split, it's got to be a doublet. And that's what this is.
Okay.
Yeah.
So-
You don't rely so heavily on chemical shifts. Yeah.
With the OH groups, you recommend you're not going to the oxygen, and you're going directly to the carbon or whatever you're attached to it. Is that what you just said? Or?
I say that again.
Okay, so with the OH group and that hydrogen, that
This one
proton
and this
attached
one?
to it? No, the OH group.
This one?
Yes.
Yeah.
You pretend like that hydrogen is attached to the carbon, like for when you're
Oh,
trying to count neighbors?
well, what you've got to be careful of is how fast is this thing coming off? And you can't predict whether these two will be decoupled or not.
Okay.
If this thing is coming on and off fast enough, it'll be a singlet. If it's not, this will be split by this, and this will be split by this,
Okay.
and these, and maybe a little bit by those.
Okay. Okay, yeah, because I was just curious, because I was kind of viewing it like, oh, well, it's attached to the oxygen, and that's like the next atom over, you know,
Yeah.
and okay.
So,
Okay? Yeah.
so in the first one we looked at on this sheet, it wasn't split, right, the OH?
In the very first spectrum we looked at,
Yeah.
those OHs were decoupled. They were coming on and off fast enough that they didn't split. That's why that sort of broadish peak is not split.
Okay.
So just to confirm, the hydrogen that's part of the alcohol is only being split by its direct neighbor, which is the carbon directly below it.
Now, if this were a double bond, there would be a small amount of splitting between here and here, but it'd be really, really tiny.
It would still be less than the single hydrogen on that carbon being split by the same methyl group, right?
Yeah, this thing is going to split that normally, assuming this is not coming on and off fast enough. If these things are coupled, this will be a doublet, and it'll split this into a doublet, but this is also being split by these 3. So each peak of the doublet is being split into a quartet.
Okay.
Mess.
Okay. So yeah.
Compound 2.
Mass spec, right? I had totally forgot about mass spec.
Oh wait, that thing we did for like an hour.
Yeah.
So we don't get a molecular formula.
We don't have
We have to
molecular formula,
formula.
that's right.
So 134. I think my formulas. I wrote that somewhere.
If there were 10 carbons in that thing, that's 120. By the way, are there any heteroatoms in that?
Anyway,
Non-carbon hydrogen atoms? Nitrogens, oxygens, fluorines, chlorines,
Doesn't
bromines?
look like it.
it looks like a ring and alkane.
Okay, look at the mass spec. Do you see any
There's no-
indication that there are heteroatoms?
There's-
Nitrogen?
There's no iodine. There's
No
no
iodine?
There's no 127. There's no couplet of like a 92 and a
That's
94.
right.
Bromine, there's no halogen.
There's none of the indications of a heteroatom are in there. So if there's a heteroatom in there, it's an oxygen.
If at all.
Yeah. Is there an oxygen in there?
No.
No. It's either, if there's an oxygen in there, it's either an alcohol, and we'd see the alcohol peak over here in the IR,
And it'd be super obvious.
and it'd be super obvious. How about if it's an ether?
The ether should be in that like 1700.
Yeah, we'd see not an ether, no, the 1700s are C double bond O.
Yeah, excuse me, that's.
Okay, so there's no double bonded oxygen, which leaves the only possibility, it's not a double bonded oxygen, it's not an alcohol, could be an ether. And then you look for the COC stretch for an ether. That doesn't seem to be there either.
But this, what's that one again? I forget.
I'd have to look up, I think it's around 1400.
Oh, right, yeah. No, I think for whatever reason.
So
it's
this thing is a hydrocarbon.
What was the ether stretch again?
I think it's around 1400. I'd have to look it up.
That sounds right.
So can you tell from that? Like, is the ether very pronounced? I forget how the peak is.
Yeah.
Could you tell if there's no ether there? I mean, there's sort of some peaks around 1400.
Well, the COC stretch is a pretty large peak.
Is it because
The
of that?
carbon-oxygen bond is a
Okay.
fairly polar bond. So as a first guess anyway, I'm going to say that it's not an ether. This is a hydrocarbon. Okay, so we know it's a hydrocarbon. Okay. What else can you tell from here?
Doesn't. It's hard to say whether there's any above 3,000, but it doesn't.
Yeah, it is.
It looks like maybe.
It looks like there could be. If there are, there are not very many of them, but okay. What's the if that's a hydrocarbon? What's the empirical formula?
It can't be C9, it has to be C8.
If it's C10, 10 carbons are 120, so that would be C10H14. Okay, so it's either C10 H14 or C9 H26. Nah.
Really hard to fit that.
Completely saturated, this thing would have 20 protons on it. 2 times 9 plus 2. So it's C10H14.
Exactly like this elements of unsaturation.
Yeah, so how many elements of unsaturation? Four elements of unsaturation.
So that means there's
It's a ring.
Yeah, so the first
Yeah.
thing you guess is, oh, let's see if it's a benzene ring.
There's a 700-ish.
So we'll go to the NMR, and sure enough, right at 7, so this is another benzene ring. That's 6. So it's a benzene ring with 4 additional carbons. Substitution pattern.
So looks like the integration. The,
12, 12, and I think this says 17.
24.
Yes, 12, 12, and 17. And these two, these are triplets. Oh yeah, here's this one, and oh, this is a quartet. 2, 7, yeah. Yeah, this is a quartet, and this one is a triplet. Yes.
So how do you do 41? You just,
Well, the integration is not necessarily exact. We've got 12, and 12 is 24, 34, 41.
Yeah, and then,
So it looks like we've got what, 14 hydrogens?
Yes.
Okay, 14 into 41 is what, 3? Yeah. If 3 times 14 is 42, that's close enough.
Okay.
Okay, so this is 4 hydrogens, so the thing is disubstituted. I would go up here now. If I had a little bit better IR, I'd go up in here to see if I could tell whether it was ortho, meta, or para disubstituted.
well, good luck with that. Okay.
That's 750 is right there, so this looks like it's about, oh, maybe 800. Can I tell you anything?
No, there's too many things to look at.
This is 780 and 830s.
Just this much on either side.
So we're looking down here,
Aromatics.
and we're looking for about an 800, 830 and 780 are right there. Okay, so that's meta or para.
But meta would have 2 peaks. So this is probably para.
Yeah, I'm going to guess para because meta, that proton on the ring would have a different chemical shift than these 3. But if it's para substituted, all 4 of those things have exactly the same chemical shift.
Right.
And you get a really sharp singlet. Okay, so now we know it's a para disubstituted benzene ring. And we've got 4 more carbons and 10 hydrogens. Okay. The possibilities are, there's only 2 of them, 2 carbons here and 2 carbons here, or 1 here and 3 there. No. If there were 1 here, no neighbors, that would be a singlet. We'd have a CH3 that integrates to 3 and is a singlet. Nope. What we have is 6.
Six. How 6?
Because this integrates to 17, and we said 3 per hydrogen. So 3 into 17 is almost 6, 5 2/3.
Oh, okay.
So these 6 hydrogens split into a triplet
So is that 2 methyls?
have 2 neighbors. Yeah, got to be 2 methyls, and because it's a single peak, they have to be exactly equivalent. They have to give you 1 peak. And then we've got 4 more split into a quartet. So the other hydrogens, the other 10 hydrogens are a group of 6 and a group of 4. And all 6 in that group of 6 are the same and have 2 neighbors. All 4 in that group are the same and have 3 neighbors.
So is
Paradiethylbenzene.
it CH2, CH3, CH2, CH3?
There it is.
Would you call it paradiethylbenzene?
Yep.
Nice.
Next.
Nice.
Oh, nice.
I like the name.
Para, di,
Paradichlorobenzene is mothballs.
Justin, is that right? Maybe the height factor?
I think so.
Okay.
This is complicated. I know. there's an N plus 2. But no, we have to have
Yeah, we've got an odd M plus peak at 117. Sounds like a nitrogen, an odd number of nitrogens.
But the nitrogen would have to have some even fragments, and we don't know.
Well, we don't know if they are.
Well, yeah, I mean, this is a little hard to read, but there's clearly a fragment at 90, probably that middle one.
Okay. So let's
Very few fragments.
Yeah.
So it must not have very many stable.
And look at the NMR.
only two big things.
Only two peaks. One of them split and the other one isn't.
Wow, look at those big dips at 700 and 740.
Okay, what is let's see if we can figure out the molecular formula. We know there's a nitrogen, let's assume there's a 1. There's only one of them. Nitrogen is 14. So we got 103, and let's subtract the extra hydrogen from the nitrogen. 102.
We're gonna have some unsaturation.
Yeah, we sure do.
Unsaturation.
We got a lot of unsaturation here because we see all these peaks above 3,000.
Is that little thing under 3,000, is that double from the aldehyde? Or is that incorrect on that?
It's not, and the reason I can tell is because there's nothing anywhere near 1,700.
Oh, right, yeah.
Okay, so we've got CH stretches above and below 3,000 wave numbers.
And we've got ring characteristics.
Yeah, and the I and the NMR, with its peak up around just above 7, suggests we got a benzene ring again.
And then we've got 2 there, so
Yeah, and
It's
this
probably
is
meta.
7 and 740, 45, something like that.
yeah, it could be mono.
Could be mono substituted.
It's kind of lines are 37.
Yeah, that's a 750. So mono. We voted
Did we decide on the chemical?
no. No, we haven't yet.
It's got a nitrogen. We should have an NH stretch up there.
And there's 2 big,
Two little things.
so there's
So it's an NH2 group,
H2.
primary amine.
That's just that 101. What else can you say?
Okay, if we take away the extra hydrogen from the nitrogen, we have 102.
And if it's an NH2, I mean, yeah, if it's an H2, we're down to 101.
Right, but I don't want to take 1 away because I want to know what the formula would be if I discounted the nitrogen.
Oh,
Okay, I'd have to take, the nitrogen counts as half a carbon, so I want to take that away.
okay.
So I take away 1 hydrogen, you got 102. 8 carbons would be 96. And 102 would be 6 more.
Mm-hmm.
So they, in the past, been looking at the, like, nitrogen group on the IR, of seeing that small of little humps, I wouldn't know whether or not I should take it into account or not.
Yeah, and that's why it's so much better to use all 3 spectra, because you're not sure here, but you go there and you see the odd M plus nitrogen. So you need to take this thing seriously. Okay, so if it's 8 carbons, we've got a benzene ring. How many elements of unsaturation? If we have 8 carbons in a nitrogen, we have 8.5 carbons. Nitrogen counts as half a carbon, so 2 times this is 17 plus 2 is 19.
And we're figuring on 7.
I thought 6.
We're thinking about 6.
Including the one on the nitrogen?
Yeah, including the one
Okay.
on Okay, so if it's C6,
Or C8.
C8.
excuse me, C8, and then the hydrogens,
You're looking at 6, but that won't work out.
let's see, 8.5, we should, if it's saturated, it's 19. This is 4 elements of unsaturation. So that brings us down to 11. We've got 8 carbons, 1 nitrogen, so that's 96, and 14 is 110.
And 7 more.
So we got must have 7 hydrogens. Substitution pattern, what did we decide?
Mono.
Okay, we decided mono substitution.
Can you run through the elements of unsaturation just one more time? My math isn't coming up.
Yeah, yeah. We figured we're going to start by guessing 8 carbons.
Okay,
So we've got 8 carbons and a nitrogen, and a nitrogen counts as half a carbon.
right.
Okay, so that's 8 and a half carbons times 2 is 17.
17
Plus 2 more is 19.
Right.
Okay, we know that we've got 4 elements of unsaturation. That should subtract 8.
Oh, that's just subtract 8. Okay.
And so there are 11 left.
Yeah, so then from there, where do you go?
Well, the next thing I did is say, okay, 6, the 8 carbons are 96. Now, nitrogen is 14, that adds to 110.
Right.
And pluses.
Our molecular weight
Is
is
117.
117, that leaves only 7 hydrogens.
But then, how would that?
Okay, if that's the case,
C8H.
and saturated would be 19, and we've got only 7, we have 6 elements of unsaturation. We've only taken care of 4 of them.
Yes, C, so. Okay.
So we got 2 more double bonds.
And you can't attach them to the benzene ring, because then you don't have room
No,
for
you
a
can't
carbon.
attach them to the benzene ring. We've decided it's mono-substituted, so that mono-substitution has to have 2 carbons and a nitrogen
And 2 double bonds.
and 2 double bonds or a triple.
But if it was a triple, then you, well, no, you wouldn't, because it would be.
No, it would have, it's only a terminal alkyne that has that spike of 3,300. So it's not a terminal alkyne.
But then, yeah, it has to be a double, because you see the CH.
Okay, now we're at the point, we're just gonna start trying things. We've narrowed it down to a mono-substituted ring. Mono-substituted, and out here we've got 2 C's and an N, and 2 double bonds or 1 triple.
And how many?
Sorry.
And 2 more hydrogens.
And 2 more hydrogens.
So let's play a hangman.
Are the hydrogens the same? Are the 2 hydrogens equivalent?
Yeah, there's
Yes.
a huge peak.
Yeah, because you've got a singlet here that integrates to 2. Any neighbors?
So No, so triple bonded C's to NH2.
Okay, so let's see what we can do. How about,
Yeah.
that work?
The IR gives you the NH2 at the 36, 37.
Yeah.
And what about that C triple bond C stretch?
Oh,
Yeah, I don't remember what it is either, but
There is.
I can look it up, and I'll bet you it's 2250, I bet you it's 2250.
Because there's a peak.
Because there's a peak in the IR of 2250, a good size peak. And this is a pretty polar bond because of that nitrogen.
Right, so you'd see that stretch
Pretty predominant, yeah.
Yeah.
Alkyne.
Right.
where would we find the C triple?
CC stretch.
It's under CC stretch 3A or 3B.
Okay, and where does it?
Okay.
So
Yeah.
it's dye substituted
Yeah,
2260 to 2190.
There it
we
is.
got one at 2250 roughly.
So is that
Okay.
one?
Okay. This is basically how you go through it.
Basically.
Yeah, you go back and forth, let's see, this spectrum tells me this, I'm gonna go over to this spectrum and see what that says, if that confirms it, and you're just going back and forth and back and forth. The mass spec will tell you heteroatoms, it will tell you the molecular weight. The IR will tell you functional groups, and the NMR will tell you numbers of protons and neighbors. Okay.